Okay, well, thank you everybody for taking time out of your schedules to join us and find out about the new and exciting features in IST 6.5. I am Pantelis Vlachos, and I'm a biostatistician in the Cytel offices in Geneva. And I will be presenting the first half of today's presentation, going through the methods that are behind the enhancements that we have added into IST. I will go initially in transition from IST 6.4 to 6.5, telling you about what has been added, what's different between the two versions, the three new modules that we have added, while my colleague Charles will also refer to some further enhancements in addition to providing you with a demo of the software. So going into IST 6.4, this is the current version of our software, for which I'm sure that quite a few of you are already familiar with. And this is the structure of the modules currently in IST 6.4. Within each one of these modules, there are enhancements that Charles will go over towards the end of today's presentation. But the focus of today's presentation is going to be three new modules that we have added. One having to do with population enrichment, one with program-level design, and MCP Mod. So let's begin by going first into the MCP Mod module, which deals in general with dose response studies. The goals of these studies is to establish proof of concept and see basically how a change in the dose results in a desirable change in the endpoint of interest. And the second goal is a dose-finding step, is one that tries to select one or maybe more than one good dose levels so that it can be passed over for a confirmatory phase 3 trial once proof of concept has been established. The current approach, the traditional approach, does this in two separate steps. So the proof of concept is conducted using multiple active arms and placebo. You have the selection of the target dose, which is the statistically significant dose at the proof of concept stage, and actually picking up the smallest of such doses, but also the one that is clinically relevant. In the dose response modeling step, data that have resulted from the proof of concept step and from earlier trials are being used, and a statistical model that captures the effects of the target dose of the dose response is being utilized. So this is a straightforward approach. It has some drawbacks, however, and mostly the drawbacks have to do with the fact that this method tends to concentrate the range of doses studied to a narrow range where the sponsors can have faith that it will establish a clear dose signal. It is also clear that the dose response model should itself play a greater role in choosing the right dose. But, however, with the current approach, the dose response modeling comes in at the very end of the process, and a much better approach would be to try and design the trial with possible statistical models in mind. So for that, the MCP Mod methodology has been developed and has been around for quite some time, and it consists of two separate components. If you view them individually, these components, the MCP component basically treats dose as a qualitative factor and then proceeds in making inference about the target dose restricted to this discrete set of doses that you used the trial. On the other hand, the mod component uses a parametric functional relationship to model the relationship between dose and response. In other words, it treats dose as a quantitative factor, and the validity of the modeling approach depends on pre-specifying appropriate dose-response models. So these two components with the MCP methodology are actually being put together, okay? And they construct the MCP Mod methodology. The difference, I'll be explaining essentially the difference in the traditional pairwise comparisons by this use of the dose-response modeling. So at the design stage, we have a pre-specification of candidate dose response models. Each of these dose response shapes in that candidate set is going to be tested using appropriate contrasts and employing MCP techniques, multiple comparison techniques that will preserve the type 1 error. Now, proof of concept is going to be established when at least one of the model tests is going to be significant. And once this proof of concept is established, either a best model, single best model, or a weighted average of a set of significant models is going to be used to estimate the dose-response profile and the target dose of interest. So, in other words, MCP Mod combines multiple comparison and model-based approaches. It tends to be robust to model misspecification, and it is quite flexible in dose estimation. So it results overall in more informative designs, and which form a solid basis for a confirmatory study, and they have been endorsed by the two major regulator agencies. MCP Mod is not new to Cytel and to our products. For the analysis part of the software, Cytel has already introduced a couple of years ago Proc MCP Mod, which is already available in the SaaS platform. What you will find in E6.5 is this new module that, besides analysis, it also includes the design, where you also have sample size and power, which are produced individually for each candidate model, but also in some summarized fashion. This design can be based on optimal allocation, and it is currently available for normal, binomial, and count endpoints. So this is the first of the three enhancements that we have made to the software. The second one has to do with population enrichment, in particular adaptive population enrichment. I'm going to be using a motivating example for this, just to provide the setup for the method that's currently being implemented within yeast. So angiosarcoma is an ultra-orphan disease. It has been poorly addressed by current treatments. Pazopanib is a VEGF inhibitor that shows modest benefit, but TRC105 can actually complement pazopanib by inhibiting endoghelin, which is a different antiangiogenic target. An adaptive trial is considered to be optimal for this type of case because this refers to a small population. We have about 1,800 cases a year. We have limited prior data. And for this particular case, there seems to be subgroup interaction because there appears to be a greater benefit possible for the addition of TRC105 to pazopanib for cutaneous versus visceral tumors. So the type of design that has been employed in such a situation is the following that you see here, and which I'm going to try to explain in the graph that you see in front of you. So we have an interim analysis. So first of all, we have the enrollment in two cohorts that will be done in a sequential manner. So accrual in the second cohort will only start after the first cohort accrual is going to be over. So the interim analysis that we have here is going to be based on patients from the first cohort only. Okay, the first cohort, these are patients, all comers, who have been obviously randomized in either pazopanib alone and pazopanib plus the addition of TRC105. Now, if the treatment shows significant improvements than the standard of care into the full population, so if we are up here, both in the subgroup and in the complement of the subgroup, no changes should be done to the trial. The second cohort will recruit the pre-specified number of subjects from both the subgroup and the complement. And then the trial will end when the required number of events from the two cohorts are going to be observed. One can think of this scenario as the full population as being in a favorable zone. So this entire design can be thought as an extension of the current sample size re-estimation procedure that is already available in yeast, which is done based on the promising zone methodology. Now, if the treatment does not show significant improvement but shows promising improvements when compared to the standard of care, then you can increase the sample size for the second cohort. Again, the second cohort will include patients from the full population, and users should actually modify just the study duration in case of treatment is promising in the full population. So in that situation, we are in this part. Now, let's go to the further down. If the treatment is not doing better than the standard of care in the full population, okay, but it's only doing better in the positive subgroup, then the new treatment is performing well. This means that there is a clear interaction between the biomarker positive group and the new treatment, and therefore, for the second cohort, we will only recruit patients with the positive biomarker only. Okay? So this scenario is when the full population is unfavorable, but the subpopulation, the biomarker positive subject, is favorable or promising. The last scenario will be when the treatment does not work in the full population as well as the positive population. This is the case when the new treatment is unfavorable in both full population as well as the subgroup. And we also have an option to stop for futility in case results are are beyond a threshold for a futility stopping. So this is the adaptive study. As you can see, there are two, as we mentioned, there are two cohorts. It's a two-stage design, so there's going to be a p-value from the data from cohort 1. There's a p-value resulting from the data from cohort 2. And we're going to be ensuring that type 1 error is going to be preserved by performing closed testing. So the closed testing uses, obviously, a combination function and a condition on the combination function, whether we are actually in the case of no enrichment or whether we are in the case of enrichment. So these particular designs are available in E6.5 for time-to-event endpoints. With time-to-event endpoints, we also have some special challenges because in order for this methodology to work, you need to have independence between the p-values in the two stages, between P1 and P2. We cannot use auxiliary data in the sense of observations of cohort 1 that become completers in cohort 2 because using auxiliary data essentially destroys the independence of P1 and P2. And this has been demonstrated in the literature. So instead of choosing the interim analysis time point to split the data in cohort 1 and cohort 2, what needs to be done is to pre-specify the allocation of the events and the sample size to each cohort before taking the interim analysis. So for example, as an example here, you can specify that cohort 1 is going to be 70 patients and 60 events. The interim analysis is going to be taken after 4 events have arrived, and cohort 2 is going to contain 54 subjects corresponding to 35 events. This allows for a full inspection of all cohort 1 data at the interim analysis, including the censored observations. And this is evaluated through simulation. This is a simulation-based approach, which means that you will get to tune your design by selecting different options, different combinations of patients and events for the cohorts, as well as the point at which the interim analysis is going to be taken. So to conclude and to recap the type of the design, we have initially the enrollment of subjects in the full population. We have the interim look. We can either proceed according to the favorable zone in the an unblinded sample size re-estimation setup where we are in the favorable zone and there's no change in the second cohort. If we have promising results, we proceed with a sample size increase in the full cohort. And if we are in the unfavorable zone, we can either fall in unfavorable for both the subpopulation and the full sample size, which means that we cannot perform any change in the second cohort, or if we are favorable with respect to the subgroup,